we'll next talk about wave superposition, which is really just a fancy way to say that waves add. So by add, we really just mean if you have one wave on a string and another wave on a string, and you've described them with some function, you just add the two functions, and that's what the string does. It just supports both waves. So you could imagine it like this. To get started, we'll just draw pulses. So here's a pulse of height A, say, and let's imagine it's moving on a string that way. And on the same string is another pulse of height A. But it's moving toward that pulse. They're coming together. Mathematically, if we had a function to describe this and a function to describe this separately, but if both occurred, we would just add the two functions. And if you added the two functions and plotted them, there would be a moment where it would look like this, right when they're on top of each other, where it would be at a height 2a, right, just for a moment. And then, if you let time progress and you still just kept adding those two functions, eventually you would have this happening. Back to height A, that original pulse going that way, and this one would be back down to A, that original pulse going that way. The pulses would just move right through each other. You can add them different ways. You could have a small pulse, say height, I'll just call it little a, and a bigger pulse, height A plus, or I'm sorry, height B, taller. They would moving towards each other. You just add the solutions. You add this function and that function, and you let them go, adding them at all times. There would be a moment when they would be even bigger, A plus B. And then if you let it go, the big wave would come out here. The little wave would go out there. B that way, A that way. So mathematically, you're adding the solutions. Physically, what it means is the waves just they ignore each other. They don't bounce off of each other. Two waves just pass right through each other. That's what happens when you apply wave superposition, when you just add the solutions. Even more interesting, what if you had this? What if you had a wave like this? Again, right now our pulses are our waves. We'll do it with waves in a little bit, with amplitude A going this way. And on the same string, you had one like that. Same amplitude A coming that way. When those two overlap, there would be a moment, just a moment, where the string would be flat. Okay? Right where this wave is on top of that wave, if you add these solutions, this plus this is 0, this plus this is 0, this plus this is 0, everything would make 0. But then if you waited a little bit longer, suddenly you would see this pulse, and this pulse would be going this way with amplitude A, that would be going that way, just for a moment. And you might look at that and say, well, if the string is flat, where did the energy go? Nothing's moving. It is moving. So remember, the wave, the disturbance propagates this way, but the string propagates up and down. So right at this moment, if you think about it, when these two are on top of each other, this part of the string is moving down, and this part of the string is moving up. So when the string is flat, it's actually still moving the whole time if you watched one in slow motion. So that's really fundamentally all we mean when we say wave superposition. Now you could ask why. Why? Why does it do this? Well, that gets into the wave equation. So one or two lectures ago, we described a wave as a sinusoid, and we used the function amplitude times the sine of 2 pi over lambda x minus 2 pi frequency time, and we said, this is this function that describes a wave. Sometimes we call that the wave equation. That's the equation that if you plot it, it makes a wave. That's not really the wave equation. That's the solution to the wave equation. It's okay to call it the wave equation, but it's really the solution. The wave equation is something you get when you apply the physics, the laws of physics to a string, and you get a big, ugly equation that we're not going to do in this class. It's usually a second order linear partial differential equation in at least 2 variables. Okay, we don't want to deal with it. But that wave equation has certain properties that make this true. Of all those words I said, second order linear partial differential equation in at least 2 variables, linear. The fact that that equation is linear is why the solutions just add. This is all really advanced stuff that you'll see some other time. Okay? But there is mathematically a formal reason why we have superposition. So I'm going to put a little star on here, a little asterisk, and say for linear waves. That means the wave equation is linear. Therefore, this happens. Some media that support waves are nonlinear, and the wave equation is nonlinear. And then weird stuff happens. In nonlinear media, waves bounce off of each other. They change their frequency all of a sudden for no reason. Lots of weird stuff. But most of the waves you're familiar with, waves on strings, sound, light, water waves, etc., those are all basically linear waves. So they all obey superposition.